I have discussed relation, types of relations, domain and range of relations, different problems based on types of relations. Today I will discuss inverse of relation. What do you mean by inverse of relation? And then after I will take some more problems. Now let us start inverse of relation. A be any set 1, 2, 3 and B be the another set. Suppose A, B, C whose elements are A, B, C. Now we have to find A cross B, Cartesian products of sets A cross B. So therefore 1A, 1A, 1B, 1C, 2A, 2C, 2B, 2C, 3A, 3B and 3C. This is the order pair elements of A cross B. Now R is the relation defined over set A to B as follows. Suppose this is the relation defined on A cross set A and B. This is the relation. This is the relation R defined over from A to B. Any relation R is defined from set A to set B. Set B. Now inverse of this relation, inverse of R, that means R inverse, it is denoted by R inverse. This equal to set of all order pair will be changed. Suppose here 1 is the domain of this R and range and A be the range of R. Therefore this is reverse. A will be the R inverse. R inverse is equal to domain will be A and 1 becomes range of R inverse. And therefore here A1, B1, 1 C1, B3. This is the A1, B1, C1, B3. This is the R inverse. Inverse of R. This is the R inverse. Therefore here we observe that the order pair should be changed. Means to say domain of R is equal to range of R inverse. Here we observe that domain of R 1, 1, 1, 1, 3 and here range of R inverse 1, 1, 1. This is the meaning of domain of R is equal to range of R. Similarly, range of R is equal to domain of R inverse. Also observe that R is a relation from set A to set B, but R inverse is relation from set B to set A. This is the meaning. Here one thing more point to be noted, that a relation R is said to be symmetric on set A and B if and only if R is equal to R inverse. This is the meaning of
Suppose a relation R is said to be symmetric if A, order pair AB belongs to R, therefore this B belongs to R. This is the condition for symmetry relation. Here order pair should be changed. Domain is the A, but in this case range will be here A. So therefore this is the inverse of relation, inverse relation, and this is the relation R, and therefore this is the R inverse. So this is the condition. A relation is said to be symmetric on a given set if and only if R is equal to R inverse. Then after I will discuss some more examples based on relation, different types of relations. So now I take some more examples like as question number 1. So that the relation R in the set of real numbers defined by R is equal to AB such that A less than equal to BA square is neither symmetric nor transitive nor reflexive. Now we construct example so that we prove this problem. Since the relation is defined over set of real numbers, we take any numbers, real numbers, and then we have to show this is not symmetric, not transitive, not reflexive. How is it possible? Let us start as follows. First of all, we verify reflexivity. Of the relation. In this case, we take real numbers. We take any real number 1 by 3 like as. So what is the condition of reflexivity? 1 by 3 less than equal to 1 by 3 का whole square. Since reflexivity condition as this is the case. Here A is 1 by 3, but we apply on this condition 1 by 3 less than B also A means A less than A square means 1 by 3 equal. This is not possible, and therefore this is not reflexive. Second, symmetric. We observe that minus 1 less than equal to 2 square, but 2 never less than equal to minus 1 whole square. Suppose minus 1, 2 belongs to R, but 2 minus 1 does not belongs to R. Hence this is not symmetric. Next, transitivity. Here we find that 2 less than equal to minus 3 whole square and minus 3 less than equal to 1 whole square, but 2 never equal to 1 square. That means 2 minus 3 belongs to R and minus 3 comma 1 belongs to R, but 2 R. This means 2 less than equal to 1 square. 2 less than equal to 1 square. This is not possible, and therefore this is also not. Hence we conclude that the given example is not symmetric, neither not transitive, not reflexive. Hence we conclude that this is not transitive. Next we take another example, so that relation R on the set of real numbers as R is equal to set of all ordered paired elements A and B such that A less than equal to B is a reflexive and transitive, but not symmetric. Similarly, in my previous examples, we also see that here solution reflexivity. For any real number A belongs to R, we have A less than equal to A. It is possible. 1 is less than 1, 2 is less than also 1, 3 is less than equal to 1, 3 is less than equal to 1, 2 is less than equal to 1 is less than equal to 1 is also possible, and therefore this implies a order pair AA belongs to R for all real number A belongs to R, and therefore R is reflexive. Suppose 1 belongs to R. This means this apply B condition, 1 less than 1 true, is also true. Suppose 2 belongs to R. This means 2 is less than equal to 2. This is also true, and therefore this is the condition for reflexivity on this relation. This A less than equal to B. Any number is less than equal to 1, less than equal to itself. Next, symmetricity. Symmetric. In this case, we observe that 2, 3 belongs to R, but 3, 2 does not belongs to R. This, what stands this? This means, and on the basis of this relation here, this 2 less than equal to 3, this is true, but 3, 2 less than equal to 2, this is not true, and therefore R is not symmetric. Now next, transitivity of relation. Since we know that A order pair A B belongs to R and B order pair C belongs to R, this imply A C belongs to R. This is the condition for transitivity. We take an example. Suppose 2 3 belongs to R and 3 4 belongs to R, this implies 2 4 also belongs to R. This means on the basis of this condition we apply here 2 less than equal to 3 true, and this means 3 4 3 less than equal to 4 also true, and this imply 2 also less than equal to 4 is also true. That means this, and that means this, and that means this. That this on the base, and this is basis of, on this basis of this relation A less than equal. Therefore R is transitive. Next we take another example, like as let A be any set of all lines, straight lines in xy plane, and let R be a relation defined over set A as R is equal to L1 comma L2 order pair such that L1 parallel to L2, so that R is an equivalence relation in A. This is the example, and relation defined over a set A, where A is the set of let A B here A B any set of all lines in xy plane, and let R be a relation defined over set A. Here we have to show that the given problem, the given relation is equivalence relation. That means we have to prove the relation is reflexive, will be reflexive, will be symmetric, and transitive. All conditions fulfilled for equivalence relations. Now we have to show one by one reflexivity. First of all, solution. Reflexivity. Since we know that any line parallel to itself, as we know, any line, so therefore suppose L be any arbitrary line in A, then line L parallel to itself, any line parallel to itself, and this is a true, and therefore this means L order pair belongs to R for all L. Since we here take any arbitrary line, so this is the true for, since this is true for arbitrary line L, and therefore hence for all straight lines, such straight lines true for all parallel to itself, L belongs to set A. Thus R is reflexive relation. Symmetric. Suppose L1 L2 belongs to set A, therefore L1 parallel to L2, as we know that this implies L2 parallel to L1. Suppose this is the line and this is the line, this is the L1 and this is the L2, L1 parallel to L2, then ultimately L2 parallel to L1, and therefore this is the condition for symmetricity, A related to B and B related to A, and therefore this is the condition for symmetricity, and this means L1 comma L2 order pair belongs to R. This means L2 comma L1 also belongs to R. This is the condition for symmetric. Hence, R is symmetric. Now, lastly, we prove transitivity. Transitivity of R. Let L1, L2, L3 all are the straight lines belong to set A. As we suppose here L1, here L2, here L3. This is the parallel to L1 and L2 parallel to L3. Therefore L1 parallel to L3. This is the automatically, and therefore we also directly we can write it as follows: L1 L2 belongs to R and L2 comma L3 belongs to R. This imply L1 directly related to on the conditions given parallelity. So suppose L1 parallel to L2 and L2 parallel to L3, therefore L1 must be parallel to L3. This is the condition for transitivity. L1 and L1 L3 also belongs to R. This means L1 parallel to L2. This is the condition given here, and L2 L3 belongs to R. That means L2 parallel to L3. This imply L1 L3 parallel to L3 also, and this is transitive, and hence we conclude that a relation which is reflexive as well as symmetric and transitive, therefore that relation must be equivalence relation, and hence finally we conclude that R is equivalence relation.